In this lecture, we will learn about damped harmonic oscillators. As we have already seen, in the case of a free harmonic oscillator, the total energy will always remain a constant. Therefore, the oscillations will never die out. But in the case of a damped harmonic oscillator, what happens is damping forces will act. Because of these damping forces, the oscillations will gradually come down, and hence these type of oscillators are known as damped harmonic oscillators. So we have already the restoring force within the system, which is acting opposite to this displacement. At the very same time, the damping force also will act together with it. So there are two forces which are reducing the oscillations. Number one, the restoring force, and number two, the damping force. This damping force is directly proportional to the velocity. So damping force F is proportional to velocity. So you can change the proportional into a constant. So F equal to minus BV, where V is the velocity and B is what is known as the damping constant. Now we will start writing the differential equation for a damped harmonic oscillator. On the left hand side, we have the representation of the force Ma, which is m into d square x by dt square. On the right hand side, we have two terms which are negative in nature. The first term is minus kx, representing the restoring force, and the second term minus bv, representing the damping force. So the equation becomes m into d square x by dt square equal to minus kx minus bv. Now the whole equation is divided by m. So what we get is d square x by dt square equal to minus k by m into x minus b by m into v. We know that k by m equal to omega square, where omega is the natural angular frequency. Now what we are going to do is, at the place of b by m, we are making a substitution. B by m equal to 2 lambda, where lambda is the damping coefficient. So the equation will be in a new form, d square x by dt square plus k by m into x plus b by m into v equal to 0, that is d square x by dt square plus 2 lambda dx by dt plus omega square x equal to 0. Now what we are going to do is, we are going to find the value of x, which is actually representing the displacement. So the method that is used is the assumption of a solution. Assume a solution x equal to a e raised to alpha t. So we will find the value of dx by dt, then we will find the value of d square x by dt square, and all these values will be substituted. We have dx by dt equal to a alpha e raised to alpha t, and d square x by dt square equal to a alpha square e raised to alpha t. So by substituting the values of dx by dt, d square x by dt square and dx, we get a alpha square e raised to alpha t plus 2 lambda a alpha e raised to alpha t plus omega square a e raised to alpha t equal to 0. We can take a e raised to alpha t outside. So a e raised to alpha t within bracket alpha square plus 2 lambda alpha plus omega square equal to 0. Since a e raised to alpha t is not equal to 0, we can write alpha square plus 2 lambda alpha plus omega square equal to 0, which is actually a quadratic equation in the form ax square plus bx plus c equal to 0. So x equal to minus b plus or minus square root of b square minus 4ac by 2a. Applying this, we will get alpha equal to minus 2 lambda plus or minus square root of 4 lambda square minus 4 omega square divided by 2, that is equal to minus lambda plus or minus square root of lambda square minus omega square. So this is the value of alpha. The value of this alpha can be substituted in the equation x equal to a e raised to alpha t. Therefore, x equal to a e raised to within bracket minus lambda plus or minus square root of lambda square minus omega square into t. Since there is a plus or minus, we can split this equation into 2. The right hand side can be split up into 2. That is x equal to a1 e raised to minus lambda plus square root of lambda square minus omega square into t plus a2 e raised to minus lambda minus square root of lambda square minus omega square into t. Now, the value of lambda and omega determines the behavior of the oscillator.